y direction is going in the x direction. And you have to worry about the signs, get signs right, and that will cause some students some strife getting the signs right. The thing is, just make sure you label your axes really clearly and draw them right on your piece of paper there, and stick to your conventions. Don't mix it up. Do not change horses midstream, right? Stick to the same axes. So, which is a strange way to say it, but anyway. And what was that? Oh, yes, but it can be more complicated. When you've got pulleys in a problem, suppose I had multiple pulleys where this thing's winding around, and you can have situations where, like if there's a pulley on this object down here, we'll see this in a couple lectures actually. When there's pulleys in a problem, you can have more complicated relationships between the positions and the motions, the velocities and accelerations of multiple objects in a problem. You can have one object moving further than the other objects when they're tied together if there's pulleys. But in a situation like this, where the pulley is just being used to change the direction of the rope, and the ropes are tied onto the objects, then accelerations are the same magnitude. The only trick is getting the signs right, given your conventions. Okay, great. So we have all these equations. Let's see. We're going to solve for acceleration. So acceleration appears. Oh yeah. So let's do this. Every place we see an acceleration, let's just call ACX. Let's just call it A, plain old A, just to simplify our equations. If we do that, then that first equation then just has an A on the end, and A2I has that becomes a negative M2A2 in the second equation, right? And the third one's a positive MCA. All right, great. So if we plug all this stuff in, we're solving for. That's what we're solving for. So let's find something else and eliminate it. What are our knowns? T1. The first equation tells us how to write T1. So what I often do is, this is bookkeeping, but I'll say, oh yeah, here's equation 1, here's equation 2, here's equation 3. I've got 5 equations. This might make my life easier to tell later on what I did when I go back to find some mistake I made or something. So let's take equation 1. And let's take these conventions and take equation 1 and rewrite it and isolate something that we want to eliminate. We're going to eliminate T1. All right, that's equal to M1. We're going to call A sub 1A, we call it A. Great. And now we have to add to both sides M1G. Keep me honest here. You got those right? Is everyone like that? I think that's right. Yeah. And the units make sense. This thing's a force, right? That's a mass times an acceleration, mass times an acceleration. I can rewrite this to make it simpler. It's M1 times A plus G. And yeah, that's good. So now I can plug that into 2. Let's see, can I? Let's see. Oh, let's do the same thing for 2, and then plug it all into 3. And that's what we do. So what does 2 give us? That's a little tedious, but I'll go quick. Here we go. T2 equals, M2 times the quantity A plus G. Oh, but let's make sure I got my sign right. I think that's a minus A, right? Does that look right? I think that's correct. I think that's right. Okay, so then we can take those things and put it all into 3. So let's give myself a little more room. Put it all into 3. What does that give me? Well, 3 now says minus T1 plus T2. Oh, sorry, that's what we're substituting in. So let's go ahead and come in. Yeah, so when I'm done, I should have only one equation with one unknown that I know it better to be A. That's what I have to solve. That's why I isolate other things first, right? Often students will isolate the thing they're looking for. They'll solve for it and then plug it in their equation, and then at the end they've got an equation. The only thing that's missing is what they're looking for. So, all right, stick in, which is what I was sort of doing there for a second. So it's minus M1 times A plus G. All right, plus, look at Phil for me up here. All right, and then what else do we need? Equals MC times, and that's just a plain old positive A. Great, and so now I've got an equation that's only got one unknown. It's A. A appears in 3 places, so I collect my terms. You guys are troopers. We're almost done with this thing. Is it minus M1, minus M2, minus MC if I'm not nuts, equals, and now I guess it's positive M1G, and it's positive, no, it's negative M2G. Everyone agree? Now when I go through all this kind of algebra, I'm going to check my answer at the end by making sure the sign makes sense, make sure that I get the right units, make sure the limits make sense. I can pull G out of that whole thing, and I get M1 minus M2, and on the bottom, I get the sum of everybody, and I just put a minus sign on the top. M1 plus M2 plus M3. In fact, I might simplify my answer by getting rid of the minus sign there and saying this is M2 minus M1. Okay, that's a lot of fast and furious substitutions. Let's see if I got the answer right. So first of all, is that the right units? So this is acceleration. G has the same units as A, right? But then look what I have over here. I've got a fraction with mass over mass. So sums of masses has units of mass. Sums of masses has units of mass. So this cancels out. There's no kilograms over here anymore. Great. The units look good. What about the sign? So let's see. This says the acceleration of the cart will be positive to your right, given my conventions, if M2 is bigger than M1. Is that sensible? Here's M2. Yeah, that makes sense. If I add mass over here, acceleration is positive. So either I must have made an even number of sign errors, right? Hopefully 0. But anyway, so what else do I have? I added 0 a few places, something like that. So great. So that looks good. What about the limiting cases? So if we let M1, we just did that. We did the limiting case where M2 is bigger than M1. Oh, and I said M3. I guess that's M cart is what I mean by that. Notice that if I change the mass of the cart, what happens? Suppose I stack up a bunch of weight on top of the cart. You don't have a big, I guess I could stand on it, but if I stack up weight on top of this cart and then add some weight, what's going to happen? Should the acceleration be bigger or smaller for the cart? Smaller. It's more massive. It's like I had a Mack truck up there instead of a VW, right? Bug, right? So that makes sense that it's in the denominator for the acceleration. The bigger this mass is, the less acceleration I'm going to get for the same M1 and M2, right? Makes sense. What else should I check? Oh yeah, if I make gravity bigger. Suppose I turn up the strength of gravity. Does the acceleration go up? Yeah, you should. Right? So good. The limiting cases all make sense. This equation seems right. Now this isn't exactly the problem I had written on my notes to solve. You saw me do all the algebra, and you see me make mistakes. The way I fix it is by going through that. I try to be disciplined to do it every time. Plus, I often learn things by thinking it through when I look at my answer that informs me about the next problem I solve. So it's worth thinking through the answer. I'm trying to think of what else we might check about here, but I guess that pretty much covers it. Great. So that's interesting. And we can also ask the question, what are the tensions? So now we can go back and solve for the tensions and see exactly what their values are. Because we've got the formula for the acceleration. We can just plug it in right here. And what we find is that just looking at this, right, the tension is going to be T1 and T2 no matter what acceleration you have. So, I take this big awful formula, I can stick it in for A in these places. But before I even do that, in fact, I'm probably not going to do it right now. But if I were to do that, this would be the same as that. And then I get some expression that's got a, oh, I see, but they have different signs. Oh, I may have to really see how this works out. I want to see if we can see right off the bat which tension is going to be bigger as a function of which mass is bigger. Well, I'll tell you what. My inclination is, let's do it real quick and see if we can get a quick answer out of it. One thing I definitely want to get to today is talk about friction on inclines and see how that affects acceleration. We've done a little bit with inclines so far, but we should do a little more before you see problems on it. All right, so let's do it real quick. Let's solve for T1. All right, what is T1? It's M1 times A. Well, that's M1 times, what is A? It's right here. It's M1G times M2 minus M1. And now I divide, oh, sorry, no, what am I doing? See, I told you I made a mistake. All right, one more time. So T1 equals M1. If I were doing this on a test or something, I'd probably write the original expression out again before I plug it in, rather than trying to do it from memory. But I'd say, okay, what do I have? I have M1 times A. A has a G in the front. So why don't we just pull G out in the front, right? Because now both terms have a G there. I get M2 minus M1 over the sum of all these guys, right? Easy to remember that because we talked through it, so I have a good feeling for what this formula looks like. And now I want to add something, right? 1. I pulled g out, right? So I said, okay, this is just 1 times g. This thing is just this fraction times g. And I need a minus sign. No, I don't. It's t1 I'm doing, not t2. There's no minus sign. So I think this expression is correct. Let's see if we simplify it, because I can't look at this and I get an idea for what's going on. So if I'm going to add 1, what does that mean? I just add a fraction that's got this denominator in it. What does that look like? m1g times m2 minus m1 plus m1 plus m2 plus mc all over m1 plus m2 plus mc. Oh, I see. The m1s cancel. That's nice. m2s combine, and now I get m1 times g times 2m2 plus m cart, right, over m1 plus m2 plus m cart. Does everybody agree with that? What does that tell us? So can I tell from this off the bat? Can I quickly figure out what t2 must look like? Well, t2 is the same thing, except that I have a minus sign in front of the acceleration. So that was minus. If that's the case, then that just changes which of these two guys is minus and plus, which means I get the same formula here, except that I get 2m2 on top. So I get m2 times g. Do you believe me? Yes. Times 2m1 plus mc, or I'm really going fast and furious to see if this works. Very good. So now I've got two expressions. Can I eyeball which one will be bigger as a function of mc? So what I should do is take the difference between, this is too much algebra for class, I'm sorry. So if I take the difference between these two guys, the ratio, I can see whether or not one should be bigger or smaller based on that. I don't know if I should continue with this. Well, I'll tell you what, I think it's clear how to go about it. There's always a trade-off in class between like showing how to solve things and going so far with it that I just bludgeon you into subconscious or unconsciousness. So why don't I leave it at that and say that, that in general, you're going to have problems where the way you're going to solve them is by looking at the individual parts. And if you're clever, you can often find a way to break it up. Like for this problem, you could have solved this. There's a way to solve it. If all you care about is the acceleration, there's a way to solve it that doesn't actually require you to do the individual pieces. To get the tensions, you still have to go through some algebra to solve it. Real quick, let me tell you how you get the acceleration if you didn't want to solve the individual parts. You could just say, well, you could think of this thing as one object that's all accelerating rigidly together. You could take a mass 1 and mass 2, sort of straighten it out, and say, well, what are the forces acting on mass 1 and mass 2? There's just downward gravity forces, right? You could just draw it like this and say, well, I've got m1, and I've got a tension 1, and I've got my mass cart, and now I've got tension 2, and I've got mass 2. So you could do that, and you could say, all right, well, I know the force acting on him is m2g, and now it's pointing that way in this weird world where I straightened the string out. It's probably going to be horrifying to me, but I'll do it anyway. And now if I think of this whole thing as my system, now I've got only two external forces, because the internal forces, tensions are just internal forces if this is my system. And to make this sort of legitimate, I defined an axis that kind of bends around and I straighten it out for my drawing. If you're comfortable doing this and you know how to apply it, you can use it and get quick answers, because now I can just use Newton's second law on the whole system that consists of m1 plus m2 plus the mass of the cart. And what does that look like? It says, and let's call this the positive direction, and just call it x, even though it's sort of different than what we meant by x before for the other two masses, but the cart is the same. What does that mean? That would say that, well, F equals ma, so what is net force? It's negative m1g plus m2g, right? Those are the external forces acting on the system, and that equals ma. But what m do I want? I want mass of the system. What is mass of the system here? The sum of the three masses. It's m1 plus m2 plus mc times the acceleration of the whole system in the positive x direction. And I think that's, do I get the same answer? So this says that the acceleration of the whole system then equals m2 minus m1 over m1 plus m2 plus mc all times g. Is that the same answer I got before? m2 minus m1. It sure is. So here's just one line of algebra to solve if all you care about is the acceleration, right? And the movie's starting in 2 minutes and you got your homework done. So that's the quick way to get the acceleration, but it requires you to be pretty comfortable with using Newton's second law in a case where you're saying, well, actually, this situation is physically identical in terms of the acceleration to another situation where the masses are collinear and the force acting on that guy is going that way instead of down, force acting on that guy is that way instead of down. Anyway, so this might be more advanced. It might just be confusing to people who haven't done this stuff before, but that's a useful trick to know if you. Anyway, but like I said, if you want to solve for the internal forces, the tensions, then that's not as helpful because then you have to do more work to figure out what the internal, like the equation avoided tension here. Why? Because they're considered internal forces when you consider all three as the system. So to get there, you have to go through this rigmarole if you want to go into the tension. Anyway, all right. So what about this situation? So this was all ideal pulleys, no friction, frictionless, this and that. What if you've got friction? We've already did a whole bunch on friction a couple lectures ago, but let's do a little more in the context of, you get lots of ramps and sliding blocks. Let me make this really clear. It's less than 30 degrees just to make my life easy. Excuse me, less than 45 degrees. 30 degrees is about I like 30 degrees. This is like 25, I guess, but yeah, 30 degrees is really good. Easy for me to read off what's going on, right? So I got some block up here, it's sliding, and there's some friction in this problem maybe. So there'll be some coefficient of static friction and some coefficient of kinetic friction. I'm pointing at the surface, but it's a function of this thing as well as this, but just to make it clear, it's just a friction coefficient, that's all I mean. And this guy's going to, and let's say the question is, it's sliding down the hill, and the question is, what's the acceleration? Now, if it were not sliding, then the question of what's the acceleration would be boring, it starts at 0. If it's sliding down the hill, then that's more interesting. I don't think we've solved this yet, have we? So let's work it out real quick, and then we'll make a more complicated version that's got multiples. So if this guy's sitting right here, he's sliding down the hill, let's define our axis along the direction of its motion, right? Make our life easy, so we'll call this the x direction, right? And it'll turn out, but we're also going to need it. Let's do this, x direction, and we'll define this to be the y direction. It's going to turn out that with friction in the problem, we are going to have to think about both directions, and you'll see why in a minute. Well, I'll tell you why. It's because these coefficients don't tell you the value of, even for kinetic, it doesn't tell you the value of the force of friction unless you know the normal force, and the normal force is pointing in some other direction. We may have to use Newton's second law to figure out the normal forces. In fact, that's the way we'll do it. Okay, great. So we've got this set up. We want to know what's the acceleration down the hill. So let's use Newton's second law. Oh, first let's do a free body diagram, right, of the block. What does that look like? Well, here's my little point represents the block. I've got force gravity, right? Yeah. And we've got what else? We've got what other force? Normal. Force normal. We don't know its magnitude yet, but we know what direction it points. It points at an angle theta to the vertical. And you see how to figure that out? The normal force points like that, which is perpendicular to this line right here. If I take a line that's perpendicular to this line, right? So that's a right angle, that's a right angle. Then because these lines are separated by theta, well, these lines are also separated by theta. But of course, I can just read it off because I chose theta to be much smaller than 45 degrees. So when I draw my triangle, clearly that small angle has to be theta, right? But anyway, that's how I do it formally. Then the next question is, all right, what other force is there? It's friction. Which way does the frictional force point? if you're told in the problem description that the block is sliding down the incline, which way does the frictional force point? It has to point up the slope because it's kinetic friction. The direction of kinetic friction always opposes the direction of motion. Not true of static friction. There is no direction of motion for static friction, but for kinetic friction. Now, if I have a block like this and I was sliding it up the hill, there's no problem where it's sliding up the hill, then friction is going to point that way. But if it's sliding down the hill, if you're told that, okay, you know it's pointing this way. So it's like that. Force of friction. And this makes an angle theta with a horizontal line. See that? Okay, great. So now when I go to Newton's second law for my block, and I want to do it in the x direction, what do I get? I get null force net x equals ma in the x direction. And I say, okay, what is force net x? That's equal to, the normal force, x component, plus the force of gravity, x component, plus the force of friction, x component equals max. What is the x component of the normal force? 0. What is the x component of the frictional force? Is it positive or negative? Friction points that way, right? The x-axis points that way. So the positive or negative? Negative. So this will be negative force friction. Now notice, positive force friction sub x is negative force friction with no x subscript in my notation. This is the x component of this vector. This thing is the length of the vector. So I got to put a minus sign in front of it to make sure that I get a negative number. So this is a negative number. If this thing's a positive number, so I get a minus sign right here. Use whatever convention you want. That's how I keep my head straight when I do this problem. That's 0. This thing, what's the x component of gravity? We've already done that a few times. Let's do it again. So I've got a force of gravity. A student came to my office hours and said, I didn't understand that triangle you drew on the sidelines. And another student said, oh yeah, what helps me out is if I draw it right on the diagram. So if I help you think about it, you can do this. See, there's the force of gravity straight down. I'm going to break it into components. Right? The right angle is on the opposite side of that. So this right here is mg times, well, let's see, that's theta, right? So is it sine or cosine of theta? I'm going to say cosine of theta. It's adjacent over hypotenuse, right? And this thing is mg sine of theta. Does everybody agree? Which of these is the x component? Mg cosine or mg sine? Sine. And so let's see if that makes sense. If I let the slope go to 0, if I let theta go to 0, then the component of the force of gravity down this incline should go to 0. And that's what happens. If theta goes to 0, sine theta goes to 0, right? Great, that goes to 0, right? Keep my head straight. I always think about it 2 different ways before I proceed, so I don't have to waste all that pencil that I paid for. Okay, great. So now what comes next? I got minus that force friction, and oh yeah, force gravity. Oh yeah, we figured out what this is. And is it positive or negative, the force of gravity, the component in the x direction? It's positive, because I can find my x-axis to go downhill. So that's right. So I get positive mg times sine of theta minus the force of friction in the right, good, equals mass times a. So here's the unknown. Here's what we're looking for: acceleration. But we don't know what this thing is yet. But we've got a formula for that. We know what the force of friction is. And is this kinetic friction or static friction? It's kinetic. It's moving, right? That's equal to mu k. So if the problem gave me 2 coefficients, it might give me 0.5 and 0.3 for my 2 coefficients. The smaller one is going to be the kinetic one usually, right? Well, always in this class. And I multiply that by the normal force. What is the normal force acting on that block? Do we know yet? Some of you probably do. And the way you solved it was by using Newton's second law in the normal direction. Okay? So in this problem, at the outset, we don't officially know, right? The problem doesn't tell us what the normal force is. But this problem is pretty simple in the sense that there's only 3 forces acting on the block. And only 2 of those forces have a normal component. The frictional force doesn't have any normal component. Only the gravity and the normal force itself, right? There's only these 2 forces. So in fact, and what is the acceleration in the y direction of the block? 0. It's not taking off in outer space, and it's not boring into the hill, right? So that means that it's got 0 acceleration in the y direction. So if you do Newton's second law in the y direction, we get, what is it? Positive force normal minus mg, and now look, it's cosine theta, the normal component, right? The y direction component, minus mg cos theta, right? So I take those differences, that difference and I set that equal to m times a in the y direction. But you've already told me acceleration in the y direction is 0. So right off the bat, I say, oh yeah, the normal component, it just equals mg cos theta. And that's what many of you probably already know that, because we saw this before. So we solved the problem without friction before, and we got the same answer. The fact that there's friction in the problem doesn't change the magnitude or the direction of the normal force acting on the block, because friction only points in a direction perpendicular to the normal direction, right? So that's good. That means our intuition holds from the last problem we solved without friction. We did that a few lectures ago. Okay, great. So I can plug this back into here. Now what do I get? Well, let's label our here. This is equation 2. Here's my equation 1. Pretty busy board. Let's go to a new spot. So we take 1 and 2. Also, I was thinking about back in my last lecture and said, what was that funny symbol? What does that mean? I had some symbol on the board. It was an and sign, but I just drew it. In my haste, it looked like, I don't know, disfigured person or something. It was a strange symbol. So I'm trying to draw it more carefully. This is what I meant to look like. The General Mills sign. You know? All right. So what am I looking for? Yeah, I'm combining equations. What do I get? I get mg sine theta minus mg cos theta. Did I get that right? I think I got that right. Equals, excuse me, is it minus or plus? Yeah, it's minus. Equals m times a. Yeah, it's very hard to do this looking at the board here from a distance. So I think I got that right. Here's my equation 1. Right, so there's a difference. There's a minus sign here. There's no minus sign here. So the minus sign survives. You get mg sine theta minus mg cos theta equals m times ax. So if I solve for, so first of all, what do you notice? So what happens to the mass? Oh yeah, people are raising their hands. I messed something up.